Hello and welcome. In today's video, we will explain the tool CNN Explainer, which implements the tiny VGG architecture, which is just one convolutional layer, as you can see in here, and a ReLU layer, then a convolutional layer, then a ReLU layer, then max pool, convolution, ReLU, convolution, ReLU, and then lastly max pool. And at the end we have a classifier layer that classifies into 10 different classes. As you can see in here, we have 10 different categories or 10 different classes. The first category is boat, the second category is this ladybug, and then pizza, pepper, bus, koala, cup, and then we have this, which is orange, and then we have sport car, and etc. So we have 10 classes that we want to classify into. The first thing we need to notice is that the input is 64 in height, so the height of the images is 64 and the width of images are 64, and then we have 3 color channels, which is red, green, and blue. As you can see in here, we have red channel, green channel, and a blue channel. The first layer receives these 3 channels. So as you can see in here, we input to the neural network, we input 64 by 64 by 3 dimensions, and then the first layer applies a mathematical operation called a convolution. Now if we click on this neuron or hidden unit, you can notice that this layer is doing now what is called as a convolution operation. The convolution operation implements a kernel or applies a small matrix, a small filter, a small window called a kernel or filter. This kernel contains weights. These weights start, as you can see in here, if you hover over this square, there's a pop-up that shows at the top of this tool. Okay, if I move the cursor, it will disappear, but we have to keep the cursor on this box, on this square, as you can see in kernel. Now this kernel contains weights or parameters or coefficients. These weights, you have to keep in mind that these weights start randomly using some initializer, whether it was Xavier initializer or he initializer, or just start randomly as zeros. We start these weights randomly, and then we use some algorithms in AI, in artificial intelligence, for example back propagation and the algorithm called gradient descent. These algorithms try to adjust, try to modify and alter and fine-tune these weights to better represent our data. Okay, so this is the first thing I want you to understand. We have the first layer called convolution layer. The convolution layer applies how many filters? Applies 10 filters, applies 10 different kernels. Each kernel contains a different set of weights, a different group of weights, and these weights start randomly, and then using the power of deep learning, the power of backpropagation and gradient descent, we try to optimize these weights to better represent the data. Now, if we click, for example, on this neuron, it will do the second kernel, the second filter. As you can see, it's now scanning over the image. It's moving across the entire image, one by one. What convolution does behind the scenes is that it does the dot product, or it computes the dot product between the values in the kernel and the input pixels. So it tries to multiply the weights that is within or inside the kernel, multiplies it by the input pixels of the image, and then it creates or produces what is called as a feature map or activation map. Okay, so the first layer, if you click on this, you will go down and you will notice that there's a section on convolutional layers, which is nice. Now let's read a little bit about this. What does it say? The convolutional layers are the foundation of CNN. So the convolutional layer is the core building block of a CNN. There is no what is called as a CNN architecture that contains no convolutional layers. Each CNN architecture or every CNN architecture must contain a convolutional layer, at least one convolutional layers, and it can be hundreds or thousands of convolutional layers. Okay, so the convolutional layers are the foundation of CNN as they contain the learned kernels, weights. These kernels extract features that distinguish different images from one another. So the job of the kernel is to detect the hidden features, the hidden patterns within images, to find out what this image contains. Does it contain edges or corners? So the kernel or the filter tries to learn, first of all, edges, the edges or the borders of the objects. So for example, if you search for an image, for example, of an airplane images, now the first time the kernel moves across this image, it tries to learn these edges, the edges of the plane. And then the second time, the second convolutional layer, it tries to learn the corners of the object. And then it learns the texture of the airplane. And then tries to learn the shapes, some simple shapes. For example, this is a triangle-like shape. This is a square or rectangle-like shape, and so on, until that it finds the most generalizable patterns that the model can generalize to a wide range of airplane images. Okay, so convolutional layers are the foundation of CNN as they contain the learned kernels, weights, which extract features that distinguish different images from one another. This is what we want for classification. As you interact with the convolutional layer, you will notice links. We have some links. If you scroll up now, once we hover on any of these neurons, you will notice that there is some links. Once we hover over it, we have some links or some connections. Now we have some links, as you can see. As we hover over any neuron in the first layer, we always have 3 connections. Now you might have the question, why do we have just 3 connections? Because the input to the convolutional layer, to this specific convolutional layer, is just 3 channels. We have red channel, green channel, blue channel. But after the convolutional layer, the first convolutional layer is done and it moves through this ReLU layer, notice we have just 1 connection. Because every neuron, we apply on every feature map of these feature maps, we apply on it a nonlinear activation function, which is ReLU. So ReLU is a nonlinear activation function that allows the model to learn non-linear relationships, allows the model to figure out non-linear correlations, non-linear relationships. Okay, and then we have another convolution layer. Notice now when we hover over this neuron, we don't have like the first layer, just 3 connections. But now we have 10 connections. So all of these neurons, as you can see, once we hover over this, all these neurons have or has a connection to this specific neuron. Why? Because now, if you notice here, we have 10 channels. We have 10 feature maps that relate to every single neuron of these neurons. Okay, so this is the first thing. Now, if you continue reading, as you interact with the convolutional layer, you will notice links or connections between the previous layers and the convolutional layers. Each link represents a unique kernel. So each connection, each line of these lines represents a different kernel. So this is a kernel, this is a kernel, this is a filter, and so on, so on. Okay? And each kernel contains weights. Each link represents a unique kernel which is used for the convolution operation to produce the current convolutional neurons output or activation map. So another name for feature map is activation map. The convolutional neuron performs an element-wise dot product with a unique kernel. So every convolutional layer applies a kernel or a filter on the input image, and this kernel applies an element-wise dot product, okay, with a unique kernel and the output of the previous layer's corresponding neuron. This will yield as many intermediate results as there are unique kernel. Okay, so however or whatever or how many kernels do we have, it will generate how many feature maps it will generate. So if you have 10 kernels, it will generate 10 different feature maps. If you have 20 different filters, it will produce 20 different feature maps, and so on, so on. So the convolutional neuron is the result of all the intermediate results summed together with a learned bias, okay? For example, let's look at the first convolutional layer in the tiny VGG architecture above. So this architecture, this kind of architecture is called tiny VGG, okay? Because we have one convolution layer and then followed by a ReLU, then we have convolution followed by ReLU, then max pool. So after each two convolutions, we have one max pool, and then convolution, ReLU, convolution, ReLU. If we just decrease the size, you will see that we have a max pool after this. So we have just two blocks. This network contains two blocks. The first block is this thing in here, as you can see. The first block contains two convolution layers. This is the first block, okay? This is the first block. We have, if you grab the pen here, this is the first block of the network, which is one convolution layer, then followed by a ReLU, one convolution, followed by a ReLU, and then lastly a max pool. So every two convolutions are followed by one max pool. And also we have here the second block. This block contains also one convolution layer followed by a ReLU layer, one convolution layer followed by a ReLU layer, and then a max pool layer. And then lastly we have this output or classifier layer. This classifier layer classifies into different classes or different categories. If we search in here VGG architecture, you will notice that the VGG architecture or the original VGG architecture is different from what is here, because this is just tiny VGG. But we have in the original VGG architecture, we have this architecture. If you search for this, yeah, I want this. Now, I want you to notice that here we have, for example, this architecture. We have the input image, for example, a car. This is an input image which is of size. If you open this image in a new tab, so open image in new tab and explain the architecture as we go. So the first thing in here, we have this image, okay? Just waiting for it to load, and then we will explain the VGG architecture. So if we continue reading until it loads, you will notice that, for example, let's look at the first convolution layer in the tiny VGG architecture above. Notice that there are 10 neurons in this layer. Okay, we have counted it before. We have 1, 2, we have here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have 10 neurons. In CNN name, we call it 10 filters, 10 kernels. So if we want to use the glossary of CNN architectures, we use the name filters or kernels rather than neurons. So we call it filters. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 filters or kernels. Okay? Notice that there are 10 neurons in this layer, but only 3 neurons in the previous layer. Because we have just 3 neurons in the previous layer, which is the input layer. Here we have the input layer. Therefore, each neuron from these neurons or each filter receives 3 channels. Okay, just 3 channels. Hence why we have here 64, 64, 3. But when we go to the second convolution, it will receive 10 incomes or 10 inputs. Each filter will receive 10 inputs or 10 inputs to this filter or kernel. Okay. Now, if you continue reading, you will notice that but only 3 neurons in the previous layer. In the tiny VGG architecture, convolutional layers are fully connected, meaning each neuron is connected to every other neuron in the previous layer, focusing on the output of the topmost convolutional neuron from the first convolutional layer. We see that there are 3 unique kernels when we hover over the activation map. As you can see in this image, this GIF image, they apply, or when they click on this neuron, for example, it will show the convolution operation, and this kernel is moving across the image, and just have 3 unique kernels: 1, 2, 3, red, green, blue. Now we have important hyperparameter. The size of these kernels is a hyperparameter specified by the designers of the network. So in machine learning, we have 2 types of parameters. We have parameters and we have hyperparameters. Parameters are the numbers, the weights, the patterns, the coefficients within the model, while hyperparameters are those settings or configurations that the machine learning engineer need to set, or the data scientist need to set before training. Before training the model, we need to set these hyperparameters. So in order to produce the output of the convolutional neuron, which is activation map or feature map, we must perform an element-wise dot product with the output of the previous layer and the unique kernel learned by the network. In tiny VGG, the dot product operation uses a stride of 1. Okay, now if you notice in here, this architecture VGG, I want you to focus now. We have one input image, or we have this input image. This is a color image, meaning it's not a grayscale image, it's a color image. And this image is of size 224, or height 224, width 224, and 3 color channels. So we have the height 224 by the width 224, and then we have 3 color channels. And this image is RGB image, meaning it's a color image. We have 3 color channels: red channel, green channel, and a blue channel. The first layer in here, notice that every block or every kind of every square that is of color gray, it will be a convolution plus ReLU. Okay, so this layer now is a convolution. The first layer here is a convolution layer. Okay, and then the second one here is a convolution. If you choose now this, for example, if you take this, for example, now this layer, which is the first layer here, is considered a convolution plus ReLU. If you change the color to red, now you will notice that we will have the first layer as a convolution layer. So this layer is a convolution plus ReLU layer. And then the second layer is also another convolution plus ReLU, as we have in here. We have in the tiny VGG, we have one convolution layer followed by a ReLU. Here we have convolution plus ReLU. Okay, so we have this convolution plus ReLU. This is another layer which is convolution plus ReLU, and then followed by this red layer which is max pooling. So this layer is a max pooling. Max pooling is a regularization layer that tries to reduce the number of computations, to reduce the number of parameters within the model. So if you want to decrease the number of parameters, hence decrease the number of computations, because every single parameter means one single computation unit. So every parameter will yield into more computations. So we need to reduce the number of parameters, hence we reduce the number of computations being done inside the model. So one max pooling layer, and then we have convolution plus ReLU layer, and then we have convolution plus ReLU layer, then we have max pool. So this is the tiny VGG architecture until here. Until here, this is called the tiny VGG architecture. But if you want to continue, convolution, max pool, convolution, max pool, convolution, convolution max pool. This is called VGG16. This is called VGG16 architecture, because we also have another architecture which is called VGG19. And you will notice that the only difference in here is that in this architecture, if you choose this, in this architecture, instead of 3 convolutions, we have 4 convolutions. If you just open this image in a new tab, note that we have input image of size 224, 3. So this is a common size in computer vision. The researchers used to use this size, which is the height 224 and then the width 224, and then we have 3 color channels: red channel, green channel, and blue channel. The first layer is a convolution plus ReLU. Okay, this architecture is confusing here because they haven't written here convolution, but it is a convolution plus ReLU. So we have convolution plus ReLU, convolution plus ReLU, then we have another max pooling layer, then convolution, max pooling, then we have 4 convolutions, 1, 2, 3, 4, followed by 1 max pooling, then 1, 2, 3, 4 convolutions, followed by 1 max pooling, and so on, until we have this fully connected layers. These fully connected layers try to discover more fine-grained patterns or more fine-grained parameters to help and improve the scalability of the model. So we have fully connected layers, which is one layer that has 1024 neurons, and then we have a ReLU layer, then we have feature collection, which is the softmax layer. Okay, so this is fine-tuned architecture. If you continue to read through here, now what I want you to notice in here also, that we have in ReLU, or for example when we choose, for example, let's choose the cup image. Now this will change into a cup. If we now choose, for example, this neuron or this filter, it will apply the convolution. And if we, for example, click on this, it will open this window. Now notice that we have in here, we have a small window or a small filter that is convolving over the image. Now it's moving across the entire image, starting from left to right and going from top to bottom. If we try to hover over, as said here, hover over the matrix or the matrices to change kernel position, if you hover over this, you will notice that this is the input, which is 64 by 64, and the output is of size 62 by 62. Convolution always decreases the size of the input. Always decrease the size of the input. So if you don't want to change the size of the input to be lower, we need to use a hyperparameter that is padding. Padding tries to conserve or protect the size of the image. Okay, but here in VGG you will notice that they are not using any padding. They are not using any padding. So the padding here is called valid padding, also known as no padding. Okay, so we have this kernel. If we change the position of this kernel, you will notice that each time we change it does some operation here. So the operation in here is multiplying the input pixel by some weight. The thing in here that the weights inside this kernel, the parameters inside this kernel are shared. The type of weights in here is called weight sharing. All the image shares the same set of weights, and you will notice that when we change this position, the pixels are changing, but these weights are the same weights. They are not changing, and this is called parameter sharing. If you search in here, what is convolution operation, and go to the IBM, what is convolutional network, for example, convolutional neural network, and go to the IBM blog post, you will read that these weights are shared by all the entire image, meaning they are not changing. Okay, so what are convolutional networks? And if you read in here, convolutional networks use three-dimensional data, images, for image classification and object recognition tasks. And if you scroll through here, you will find that how do convolutional networks work. Convolutional networks are distinguished from other networks by their superior performance with image, speech, or audio signal inputs. They have three main types of layers, which are, there are three main types of layers in any CNN. Convolutional layer, followed by pooling layer, and then fully connected FC layer or dense layer. So every CNN architecture should have this type of architecture. If you search, for example, for the first CNN architecture in the world, which is Linet 4 or 5, okay? This architecture was found by Jan LeCun. Now, if we zoom into this architecture, you will notice that we have input image of size 32 by 32. For example, the letter A. This is a grayscale image. The first thing we have in here, convolutions. So we have convolution layer followed by subsampling. At that time, when they found this architecture, there was no max pooling. So they used to name it subsampling. So it was called subsampling. It wasn't called max pooling. So convolution followed by subsampling, which is now called max pooling, and then we have convolution, then we have subsampling, followed by this fully connected layer. This fully connected layer, okay? So this is the FC layer, contains 120 neurons, and this layer contains 84 neurons, and then the output layer contains 10 neurons. So this is Linet 5 architecture. Convolution, subsampling, convolution, subsampling, then fully connected, fully connected, fully connected, then we have the output in here. And also, if you search for example, AlexNet, you will notice that we have the same set of layers. We have convolutions, and then we have max pooling. Architecture. We have convolution, then we have max pooling. In this type, we have convolution, 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 and then followed by fully connected layers. So these are the main types of layers in any CNN. We have one convolution layer, followed by a pooling layer, followed by fully connected FC layer. The convolution layer is the first layer of a convolutional network. While convolution layers can be followed by additional convolution layers or pooling layers, the fully connected layer is the final layer. With each layer, the CNN increases its complexity, identifying greater portions of the image. Earlier layers focus on simple features. So the earlier layers of any CNN focuses on simple shapes, on edges, corners, textures, while the later layers tries to learn more complex shapes. For example, triangle-like shapes or rectangle-like shapes, such as colors and edges. As the image data progresses through the layers of the CNN, it starts to recognize larger elements or shapes of the object until it finally identifies the intended object. Convolution layer. The convolution layer is the core building block of a CNN, and it is where the majority of computation occurs. It requires a few components, which are input data, a filter, and a feature map. So any conv layer requires an input data, a filter, which is a small matrix, and a feature map, which is the result of the convolution layer. Let's assume that the input will be a color image, which is made up of a matrix of pixels. So we need to turn the image, any image or any color image, we have to turn it into a matrix of pixels in 3D. Why 3D? Because we have the height dimension, the width dimension, and the depth dimension. The depth is the color channels. So this means that the input will have 3 dimensions, a height, width, and depth, which corresponds to RGB in an image. We also have a feature detector. Another name for the filter or kernel is also a feature detector, because it tries to detect the features or patterns, also known as a kernel or a filter, which will move across the receptive fields of the image. So the region that the kernel covers is called a receptive field, or called a patch. Checking if the feature is present. This process is known as a convolution. The feature detector is a two-dimensional 2D array. So the filter or kernel or feature detector is a two-dimensional 2D array of weights. So this square in here that we move now is a 2D array. It's a 2D array. It cannot be 1D array. It has to be a 2D array of weights that contains weights and multiplies these weights that are fixed, that are not changing, multiplies it by the region that it covers. Notice that these pixels are changing when we change the position. These pixels are changing while these weights are not changing. Okay, this dot product is then fed into an output array. Afterwards, the filter shifts by a stride. In TinyVGG, we shift this stride by 1 pixel. Okay, while in other architectures, there are different stride lengths. For example, if you search for AlexNet architecture and go, for example, to here, note that we have here stride is 4, s equals 4. In the second convolution, stride equals 2, and here same, stride equals 2, and here stride equals 2. Okay, so the stride is 2 in AlexNet, but in VGG we have stride of 1. Now this 2D array, which represents part of the image, while they can vary in size, also the kernel size can vary in size. So we might have a kernel size, for example, in AlexNet, we have the kernel size. If you open this image and go into here, we have this kernel size 11 by 11. And in VGG, the kernel size is different. If you search for VGG now, architecture, we have a kernel size of, here we have the kernel size of 3 by 3. So the kernel size can change or can vary depending on what you choose. Kernel size is an important hyperparameter. Also in this tool, if you search or if we scroll down here, we have this important section. This section is very, very important, and it's also a fun section to play around with. Now we have input size of 5. If we try to increase the input size to 7, we will have the input size of 7. And now you'll notice that the kernel size here, kernel size, filter size, feature detector size, window size, whatever you like to call it, if we change it to, for example, 1, you will notice that we have just 1 kernel size. So the kernel size now is 1. So the kernel just covers 1 pixel. When I say that the kernel size is just 1, that means it just covers 1 pixel at a time. It covers 1 pixel at a time. So 1 pixel, 1 pixel, 1 pixel, and when it covers this 1 pixel, it produces an output feature map, and this is the result of this. Then this is the result of this step. If we move along, we have different results, and we will and by convolving on the input image, we will produce a feature map, another matrix, a new matrix, a new 2D matrix, which is called feature map or activation map. Okay, if we change the kernel size to 2, we will have a 2 by 2 kernel size. Now it covers 2 rows and 2 columns, and the result is also a one value. So the result of multiplying the kernel weights by the input image is just a single value. Okay, that's why we have here, if you scroll up, we have, when we choose this, we have the output of any convolution is just equals 1 value. So this is the first weight multiplied by the first input pixel, plus the second weight multiplied by its corresponding pixel value, and then the third weight multiplied by its corresponding pixel value, so on, so on, so on, and then the result of this convolution operation is just 1 value. But this 1 value, when we move across the entire image, we will have a new matrix. It will produce a new matrix called feature map. Now this kernel size, when it hovers over each region of the image, it will produce one value. Okay, hence why we have here just one pixel colored. Even if we try to increase the kernel size, we will also have just one output value. The next thing, or the next important thing, I want you to notice that the lower the kernel size, the bigger the output. So now the input size, always in machine learning, there's a chief problem in machine learning called input shapes and output shapes. Inputs and outputs. The most important and the most significant, or the major problem in machine learning. Most machine learning engineers pay attention to input shapes and output shapes. So the smaller the kernel size, the bigger the output. If we have a kernel size of 1, then the output size will match the input size. Okay, now we're not focused on the padding. The padding will affect on these shapes. But now if we zero the padding, if we make the stride normal 1 and just play around with kernel size, the smaller the kernel size, the bigger the output. And when the kernel size is 1, the output will match the input. But if we try to increase this kernel size, you will notice that the output is 6 by 6. So the output is smaller than the input. And if you increase also more, the output is 5 by 5. Okay? More, the output is 4 by 4. Now we have a kernel size of 4 rows and 4 columns, and it covers a big region or a big area of the image. Then if you try to increase the kernel size until we have just one output, just one pixel in the output. Why? Because the kernel size match the input size. When the kernel size, for example, 7 now, and the input size is 7, so it covers the entire input, it covers the whole input, then it will produce just one scalar value, which is the output. Okay, so this is the kernel size. Now if we try to decrease the kernel size to a normal size, for example 2, if we read about kernel size here, kernel size, often also referred to as filter size, refers to the dimensions of the sliding window. So kernel size sets the dimensions or the size of the sliding window over the input. Choosing this hyperparameter has a massive impact on the image classification task. So the most important hyperparameter in CNN is kernel size. For example, small kernel size or small kernel sizes are able to extract a much larger amount of information containing highly local features from the input. Okay, so small kernel sizes, the smaller the kernel size, the more able the kernel is to extract a much larger amount of information containing highly local features, containing highly local patterns from the input. As you can see on the visualization above, a smaller kernel size also leads to a smaller reduction in layer dimensions. So as we said before, smaller kernel size, okay, results in smaller reduction, while bigger kernel size results in larger reduction of the output size. Okay, so a smaller kernel size also leads to smaller reduction in layer dimensions, which allows for a deeper architecture. Conversely, a larger kernel size extracts less information. You have to keep in mind that the larger the kernel size, the less information it will extract from the image. Why? Because the kernel will cover a large portion of the image and will extract just information from that area, and then it will move and also cover another large portion of the image and extract new information, while smaller kernel size will cover the same regions overlapping, regions of the image, and hence will extract much larger information or a big amount of information from the image. A larger kernel size extracts less information, which leads to faster reduction in layer dimensions, often leading to worse performance. So you have to keep in mind, this kernel size is fun to make it bigger, but you have to keep in mind that the kernel size, the bigger the kernel size, it will make the CNN architecture worse in performance, often leading to worse performance. Large kernels are better suited to extract features that are larger. So if you have large images, for example 512 height and 512 width, you may want to use large kernel size. But if you have small images, for example 28 by 28 or 69 by 69 or 96 by 96, these are small sizes, you want to use small kernel sizes. At the end of the day, choosing an appropriate kernel size will be dependent on your task and dataset, because you as a machine learning engineer, you have to set this kernel size. But generally, smaller kernel sizes lead to better performance. So this is a general rule. Smaller kernel sizes lead to better performance for the image classification task, because an architecture designer is able to stack more and more layers together to learn more and more complex features. So that is for kernel size. For VGG, the tiny VGG architecture uses a kernel size of 3. Okay, so this is 3 rows and 3 columns. We have 3 rows and 3 columns. While in AlexNet we use large kernel size of 11. Okay. Now what about stride? If you, for example, choose this neuron, you'll notice that we have 10 filters, 10 kernels, all working at the same time. Now, the important idea here is that the model learns these filters, or the model applies these filters in parallel. They are not done sequentially. So this one is done, and then we have this one playing, and then this one is waiting. No, we have all these filters running in parallel. Okay, this is an important idea. It runs them all in parallel at the same time, tries to adjust these weights and these kernel weights at the same time. Each kernel from these kernels, if you try to zoom into here, now this kernel have weights, this kernel have a different set of weights. Here we have 0.15, as you can see in the above, and here we have 0.21, and here we have different set of numbers. So these are kernel weights. Slide kernel over input channel to get intermediate result. Click on learn more. If you click on here, learn more, we will have this convolution operation is done in here. The second layer is going from the input size was 62 by 62. Now the output is 60 by 60. While the first convolution layer, the size was, if you click on this, the size was 64 by 64, and the output is 62 by 62. Now, why the output size is less than the input size? If you read about padding, you will find the cause or the effect behind this padding. Now, okay, now let's play around with padding. Now we have padding of 0. Padding of 0 means no padding. If you search in here in IBM, okay, blog post, padding. Yeah. Note in here, note that the weights in the feature detector remain fixed as it moves across the image. Okay, this is a very significant idea. Note that the weights in the feature detector remain fixed as it moves across the image, which is also known as parameter sharing. So CNN applies the concept of parameter sharing. The image uses the same set of parameters across the entire convolving operation. Some parameters, such as the weight values, adjust or modify during training through the process of backpropagation and gradient descent. However, there are 3 hyperparameters which affect the volume size of the output that need to be set before the training of the network begins. These include, so we have 3 important hyperparameters, all affect the volume size of the output that need to be set by us ML engineers before the training of the network begins. These include the number of filters. So the number of filters will will tell me the number of feature maps. The number of filters affects the depth of the output. For example, 3 distinct filters would yield 3 different feature maps, creating a depth of 3. And then we have stride. Stride is the distance or the step size. So stride, another word for stride is step or number of pixels. Okay, so stride refers to the number of pixels the kernel moves by, that the kernel moves over the input matrix, while stride values of 2 or greater is rare. So stride values of 2 or greater is rare. Why? Because if you use a stride value, for example 5 or 4 or 6, the convolution operation will not produce a feature map that is rich or full of high level features. Okay, so a larger stride yields a smaller output. Now let's try stride here. If we, for example, make the kernel size 3 by 3 as the tiny VGG, now we have a kernel size of 3 rows and 3 columns. If we try to set now the stride is 1, we move by 1 pixel. Okay, so notice that we have just 1 pixel off, then 1 pixel off, then 1 pixel off. We move by 1 pixel. And also from left to right we move by 1 pixel, and also from top to bottom we move by 1 pixel. Okay, if we change now the stride to 2, if we increase the stride to 2, now we will move by 2 pixels, and also from top to bottom we will move by 2 pixels. So the less the stride or the lower the stride, the bigger the output size. Now we have output of 5 by 5. If we increase the stride, I want you to focus in here. If we increase the stride and make it 2, the output is now less. Now we haven't changed the kernel size. The kernel size, yes, the kernel size lowers the output size. The bigger the kernel size, okay, the lower the output. Also, the bigger the stride, the lower the output size. Okay, if we make the stride here 3, but it doesn't fit because the input size is, if we make the input size of this and make the kernel size 2, now we will have a stride of 3. So notice that we move by 3 pixels. Now if you try to move, 1, 2, 3 pixels are moved upon. Okay, and also 3 pixels from the top to bottom. So this is stride. So stride is a dangerous hyperparameter. Stride indicates how many pixels the kernel should be shifted. Stride indicates how many pixels the kernel should be shifted over at a time. For example, as described in the convolutional layer example above, tiny VGG uses a stride of 1 for its convolutional layer or convolutional layers, which means that the dot product is performed on a 3 by 3 window of the input to yield an output value, then is shifted to the right by just 1 pixel for every subsequent operation. The impact stride has on a CNN is similar to the kernel size. Why? As stride is decreased, more features are learned because more data is extracted, which also leads to larger output layers. On the contrary, as stride is increased, this leads to more limited feature extraction and smaller output layer dimensions. One responsibility of the architecture designer, for example we machine learning engineers, is to ensure that the kernel slides across the input systematically when implementing a CNN. Use the parameter visualization above to alter stride on various input kernel dimensions to understand this constraint. So now we have visualized the stride and kernel size. Now if we try to play around with padding, now we have padding of 0. If we make the input size 5 as this and make the stride normal as 1 as in tiny VGG architecture and make the kernel size, for example, 3, now if we play around with padding, now we have padding 0. If we try to increase padding, now we will have a padding. when we had the kernel size, when we have kernel size 3 and stride 1, notice that the input size is 5,5, but the output is 3,3. Once we put padding, once we apply padding to the image, the output matches with the input size. So we have output size of 5,5. Why? Because now the input dimensionality is protected, is conserved. If you read through here, padding is often necessary when the kernel extends beyond the activation map. Padding conserves data, so keeps data or protects data at the borders or at the edges of activation maps, which leads to better performance. So padding leads to better performance because it tries to keep all the information have the same weights, have the same size. The data or information at the corners also have the same weight as the data or information in the middle of the image or in the center of the image. And it can help preserve the input's spatial size, which allows an architecture designer to build deeper, higher performing networks. There exist many padding techniques, but the most commonly used approach is zero padding. So there are many different padding techniques. For example, there's a technique that takes some pixels from the center of the image and put it in the top and left and bottom of the image. Uses some portions of the image from the center and enhance the image size at the borders using some pixel data from the center of the image. But the most commonly used approach is called zero padding. We use the number 0, so nothing, just black pixels. Because of its performance, simplicity, and computational efficiency, the technique involves adding zeros systematically around the edges of an input. This approach is adopted by many high-performing CNNs such as AlexNet. So AlexNet employs the zero padding approach or implements the zero padding approach. Why? Because zero padding is adopted by many high-performing CNNs such as AlexNet because it is simple and also computational efficiency. Okay, so if you have important information at the edges of an image, for example, you have some images that have very important information and data that the model could understand from its very important patterns and features, and you want to keep those data at the borders have the same kind of treatment as the data in the center of the image, you may want to look into padding. Okay, so padding is an important hyperparameter. If we increase the padding now, for example 2, we will have a larger output size than the input size. Okay, because now we have 2 borders of padding. Now if we set the padding as 1, we just have one padding border. If we increase 2, we have 2 paddings. And now the output will contain 1 padding here, and this is the real data. Here, the real data, the real image. Because this padding in here, this padding is being protected, and this padding in the outer is being eaten or being getting rid of by the convolution operation. Okay, so we just have padding 0, 1, 2. We have just 3 values. We cannot increase the padding anymore. Why? Because if we read in the IBM blog post here, zero padding is usually used when the filters don't fit the input image. This sets all elements that fall outside of the input matrix is to 0, producing a larger or equally sized output. So you might produce a larger output size, or you might produce an equally sized output as the input. There are 3 types of padding. We have valid padding. This is also known as no padding. So this might seem confusing. Why is it called valid? Because valid means no, we don't use padding. That is valid to convolve over the image without padding. So they understand it from this perspective. So valid padding, this is also known as no padding. In this case, the last convolution is dropped. if dimensions do not align, don't align. And we have also same padding. Same padding, this padding ensures that the output layer has the same size as the input layer. So same padding. Same, it also might be confusing because you might think as input size 7 by 7, output size will be 5 by 5. So we have same, the same size of the image. No, same padding tries to make the input size the same as the output size. So they have called it same. So same means the input size the same as the output size, and same is 1. Same means padding of 1. So if you have padding of 0, that is called valid padding. Now this kind of convolution is using valid padding. Okay, notice that the input is 5 by 5, but the output is now 3 by 3. But if we now this is what? Valid padding. When we have padding of 1, this is same padding because we have the same input size as the output size. So this is called same padding. And if you have 2, that's called a new type of padding. If you go into here, that is called full padding. This type of padding increases the size of the output by adding zeros to the border of the input. Okay, so now we have explained the different hyperparameters in a conv layer. So each conv layer, whether this layer or this layer, have a kernel, have a filter, and these filters try to learn the different features, edges, simple shapes, textures from the images, and these filters, the size of it is a really important hyperparameter that is set by the machine learning engineer. We set the size of this filter or the size of this kernel, and you try different kernel sizes and then choose the best or the highest performing filter size. Okay, each kernel moves by a certain amount of pixels called a stride. So each filter moves by a certain amount of pixels called stride, and this stride also is another important hyperparameter that affects the output size. The larger the stride, the lower the output size. The larger the kernel size, the larger or the bigger the kernel size, the lower the output size. And we also have padding. If you want to protect the data at the border, we also have padding. We have 3 types of padding. We have valid padding, also known as no padding. We have same padding. In valid padding, the output size is always lower than the input size. In same padding, the output size is the same as the input size because we add just 1 padding. And in full padding, the output size is larger than or bigger than the input size because we have added too many zeros around the edges. Okay, now in ReLU layer we have this kind of operation. Notice when we try to move this kernel, okay, we will have ReLU is a nonlinear activation function that is nothing but a max function, just a max function between 0 and this value. If it was negative, we will choose 0 because 0 is higher than negative. Notice here equals 0. The output of the ReLU here is 0, so no activation. Notice here we have nothing, just white pixel. But why do we have these regions in like of colored? We have some regions have white pixels. All these regions that have white, they are all negative activations. And when we apply ReLU, we emphasize the important features of the image. Here we have positive regions, okay, but here we have negative. So now this region is white because why? Because the output of the convolution was negative, and when we apply ReLU after the convolution, ReLU will choose what is the max value. Is it 0 or minus 0.44? Well, it's 0. Well, hence we have here nothing, just white region. But in this region, or in these regions that have some color, that have that have some outline, some texture. We have here positive result from the convolution layer. So these results come from where? Come from the convolution layer. The convolution layer produces these results, and we apply the max function or ReLU function, and ReLU will choose this value 0.18 because it's higher than 0, and hence this region will be activated. So we have some activated regions. These are called activated regions, while these regions are called not activated. So these regions are fired. Okay, here we also have some negative values here, and if you try to move here, we have some positive values, 0.11. Also here we have max. If we choose the max between 0 and 0.28, we have 0.28. So all these regions are positive values. Okay, if we try to choose a more clear image, for example this, you will notice that all these regions have strong activations, have strong patterns. So this filter is a really good filter because this filter is stronger than that previous filter because it has detected so much features, so much patterns. Okay, so these are all positive regions, activated regions. So if you have this very dark region, it's so close to 1. Try to find 1 point. Okay, now these regions are all activated, are all positive. So we have this kind of output here, input 62 by 62, and the output is 62 by 62. Why? Because this is just a ReLU function. ReLU doesn't change the shapes, just takes the same input size and outputs the same output size. So the input was 62 by 62, the output is still also 62 by 62 because ReLU doesn't change the size of the input. It just applies this simple function of max function and applies it on this activations. Then after ReLU we have this convolution layer. This convolution layer now learns more deeper features, more deeper patterns than this first layer. This first layer, for example, learns the edges, the textures, while this convolution layer learns some high level features or some deep features, for example, the texture, the shapes. And this convolution layer, you'll notice that the images in here are more activated, or so much activated than the images in here, or than the images in here. Why? Because this conv layer is very deep, and it tries to learn very deep patterns and features than these shallow layers. Okay, so then we have a convolution. If you try to choose this layer, it will apply this convolution operation, as you can see in here. And if you try more clear, yeah, these images are more clear or more distinguished than these images in here. If you, for example, click on this, it will apply this simple convolution operation. And if you choose this one in here, you will notice that we have this kernel size is convolving or moving across, or is going across the image, over the image, and then the input size is 62 by 62, but the output is 60 by 60. So also the convolution here tries to decrease the image into a smaller output size. The operation here is the same. We have the weights remain fixed, so we have parameter sharing. The image shares the same set of parameters, but the pixels are changing, and then we multiply each weight by its corresponding pixel, and then we sum those up. We will get a just single scalar. This scalar 0.19 is now being here 0.19, and then if we try to move the kernel across, we will have different values, and then go from left to right and going across the image and doing the convolution operation. So this is convolution here. Now after convolution we have another ReLU, the same. Then we have a max pool layer. Now let's read about what is max pool. Okay, we have read about convolution. Now let's read about max pool layer. So what are pooling layers? Why do we have to use max pooling or some kind of pooling layers? Well, if you want to search here, what is pooling layer in machine learning? We have this great blog post in here. If you search for the site built-in or deep learning, deep AI, deep AI. This is a great blog post about max pooling. If you search in here, max pooling layer, max pooling layer in machine learning, we have this deep AI blog post. What is max pooling? Well, max pooling is a downsampling technique. So it's a technique to downsample. So it's a downsampling, or as Jan LeCun have named it, it's called here, if you search for Linet 4 or 5, they have named it as subsampling. So we have convolution, then we have subsampling. Convolution, pooling. Convolution, pooling. And this image, they have called it subsampling. So you have some convolutions, then subsampling. Then you have convolutions, then followed by subsampling. So it's called downsampling or subsampling, downscaling or subscaling. These are all valid names for max pooling. So max pooling is a downsampling technique commonly used in convolutional networks. So commonly used in CNNs, okay, in CNNs to reduce. Why do we have to use max pooling? Why? What is the purpose of max pooling? The purpose behind max pooling is to reduce the spatial dimensions of an input volume. It's a form of nonlinear downsampling that serves to make the representation smaller and more manageable. So max pooling tries to make the representation smaller and more manageable. If you try to notice in here, in this architecture, as we move along or as we step through the network in here, you notice that we start bigger. We start with a big image, 62, or here we start with 64 by 64 and three channels. Then we have 62 by 62 by 10 channels. Then we have ReLU, doesn't change the shape, also the same, 62 by 62 by 10 channels. Then we have the convolution here, 60 by 60 by 10. Then ReLU, the same shape, 60 by 60 by 10. Then we have max pool, 30 by 30 by 10. Wow, that is a big decrease in the size. Why? Because max pool tries to make the representation more manageable and smaller in order for the network to capture the most significant features. Okay, so there's a pattern in deep learning. We always try to make high dimensional data. We try to convert high dimensionality into lower dimensionality. We try to convert big images into small vector spaces. Focus on important vector spaces or on important feature spaces. So we start with high dimensional textbooks or high dimensional images, high dimensional datasets, and then the deep learning architectures tries to lower them to make them smaller and smaller and smush them or make them more fit into what is called as a feature space or vector space that is small vectors but represents the high dimensional data. So then when we try to predict, we pass again high dimensional data, high dimensional images, but these small vector spaces can represent or can deal with these high dimensional data and understand what's going on in the image. So here max pooling is a technique or is a downsampling technique commonly used in CNNs to reduce the spatial dimensions of an input volume. It is a form of nonlinear downsampling that serves to make the representation smaller and more manageable and to reduce the number of parameters. Why do you want to reduce the number of parameters? Because when we reduce the number of parameters, we reduce the number of computations inside the network, okay, and computation, as you can see here, and computation. So to reduce the number of parameters and computation in the network, max pooling operates independently on each depth slice. So max pooling operates on the red channel independently, operates on green channel, operates on blue channel independently on each depth slice of the input, and resizes it spatially. So max pooling also resizes the input size, okay. The primary objective or the major objective of max pooling is to reduce the amount of information in an image while maintaining the essential features necessary for accurate image recognition. So when we pass an image through the network, this image contains some noise. For example, if you try to make the image here, or then the CNN tries to learn this bus image, okay. Now this image contains a bus, but also contains some noise, which is the trees. So max pooling helps to reduce the spatial dimensions in order just to keep the important and the center of the image, and reduce that high noise features or patterns within the image. Why? To make the CNN more able to generalize to a wide range of images. So max pooling reduces the problem of overfitting. So there's a problem in machine learning called overfitting. Max pooling helps to reduce or decrease the risk of overfitting. If we keep reading in here, so while maintaining or keeping or protecting the essential, important, significant primary features necessary for accurate image recognition. This process helps to make the detection of features in input data invariant to scale. So max pooling helps to make the CNN more smarter, more intelligent. Why? Intelligence is compression. All AI is all about how to make this high dimensional data into a more compressed representation that represents the entire image. So how can you figure out a small vector that can represent a high dimensional tensor? How can you figure out a small scalar that represents a high dimensional matrix? This is AI. AI is all about compression. Just one thing can represent a whole idea. For example, if you hear from an old man some intelligent saying, for example, don't pursue the work of today to tomorrow, you will notice that this idea is a compression to a phenomena in the universe. So intelligence or the smartness is latent inside compression. Compression is the most important thing in deep learning. All deep learning architectures tries to compress data into a more manageable and more intricate patterns. So to make the detection of features in input data invariant to scale and orientation changes, and also aids in preventing overfitting. Because overfitting is when the model, what is overfitting? Overfitting is a problem in machine learning, or is a popular problem in machine learning. So all machine learning models, all deep learning models can be overfitted. So whether it was k-nearest neighbor or linear regression, logistic regression, decision trees, support vector machine, naive Bayes, or simple dense network, or CNN, RNN, LSTM, GRU, or LLMs, generative AI, all these models can overfit. Or whether it was ensemble learning, for example, XGBoost models or random forest models, or whether it was any other model, all these models can be overfitted. And overfitting is a really important concept in machine learning. Overfitting happens when the model tries to memorize the same patterns in an image. So for example, the model tries to memorize the shape of the tree with the bus. Later, when we pass just an image of bus images without trees, for example, this bus without trees, the model will not be able to detect that this is a bus. It has to see some kind of tree. So this is noise. But with max pooling, with techniques like max pooling, or for example techniques like average pooling, we can decrease this noise in the images, decrease this unnecessary features and just focus on the important features. Okay, how max pooling works? Max pooling is performed on the convolutional layers of a CNN. It involves sliding a window. Also, max pooling, if you try to, for example, choose this image, max pooling also, notice here, we have input of 60,60, but now the output is 30,30, meaning that the input or the output is half the input. The max pooling layer always try to halve the input, make the input half. So the output is half the input. Now, if you try to go into here, now we have this kernel. Max pooling is similar to a convolution layer. It also applies a kernel, a 2 by 2 kernel. The convolution is a 3 by 3 kernel. Note here, in a convolution we have this 3 by 3 kernel. This is a ReLU layer. Okay, if we try this and try this, we have a 3 by 3 kernel. Note here we have 3 rows, 3 columns. But in a max pool layer, the kernel size is different. Here it's 2 by 2. Now, does it important to make this 2 by 2 and convolution 3 by 3? No. This is another hyperparameter that you have to try and improve by experimenting. You have to experiment different kernel sizes and choose the best performing kernel size. So here we have this kernel size, which is 2 by 2, and then max pooling just applies this operation, which is max, just the max. So it takes the max. So now, for example, here, what is the max of these numbers? We have 2.98, 3.27, 2.92, 3.1. What is the maximum value? What is the largest value? The biggest value? We have this value, 3.27, now equals 3.27. And hence, this value is being put into here. And so on, so on. So this kernel slide over the image, slide across the image, and each time it covers a region, it takes this region and operate on this region and take the max value and put it into here. And going on, just taking the maximum value, takes the max value of all the images, of all the regions that it covers. Okay, each region that it covers is called a patch. This is called a patch or called a receptive field. Okay. Now after this max pooling, we have another convolution layer. Note here, now the size in here is 28 by 28. Why? Because the input to this layer is 30,30, and then the convolution here receives 30 by 30 and then decrease it into, so it receives a 30 by 30 input and then makes the output as 28,28. Okay, so it tries to make the output smaller than the input. Now note here, we can see now the kernel clearer or more clear, because now the input image is small. Now this image is small. As you can note in here, it's just 30, the height is 30 and the width is 30. But the output in here, the output is 28 by 28, and it does also the convolution operation. Note in here, the model learns more specific features, more deep features. It learns the shapes. So this is like a rectangle shape, and then we have some dropping region here. Then we have some connected shapes in here. So these are shapes that the model can understand. We as humans, we don't understand this compressed representation. We like to look at things in a normal way. For example, a bus. But the model likes to look at these kind of ununderstandable representations. Okay? The model looks to things in the other way that humans like to look at things. Okay? So these are just convolution operation, another convolution convolution operation over the image, and then we have, after this convolution, we have another ReLU layer, then we have another convolution layer. Note in here we have very activated regions. Okay, if we choose this, we have this window in here. Note it's very activated. We have input 28 by 28, and now the output is 26 by 26 because we have applied convolution on this input. Okay, lastly we have a ReLU layer followed by a max pool layer. The ReLU layer doesn't change the shape. We have 26 by 26 by 10 channels, but the max pool now halves the input. We have 26. If we divide 26 by 2, we will get 13. So now if you choose this, you will note that we have a very small image now. Very small image. Okay, the input is 26 by 26 and the output is 13 by 13. So each region, now here we have, note in here, we have white pixels. This region is not activated. It's not an important region for the model. And that's true. Why? Because we have trees. Because we have trees, this region is not important to the model. It's being discarded. But this region is important because we have this kind of the front of the bus. The front, and then we have the body of the bus in here. Okay, so the model tries to learn these representations, these features, patterns, or hidden configurations behind these images, and then can be able to classify these images correctly. So that's the art of deep learning. Now, if we try to go in here, all numbers are 0. Also here, 0, 0, 0, and the max of 0 is 0. But if you go to this activated region, you will notice that we have some numbers, and then the max pooling tries to calculate the max value. It calculates the max value. So the max value here is 2.18, and then outputs this value into here. So the inactivated regions will result in also in activated regions, but activated regions will result in also activated regions, and that's why deep learning, the deep learning network, will be able to figure out the more specific features around the shapes in the image. The last thing in here, we have this output layer. This output layer contains 10 neurons because we want to classify into 10 classes or 10 categories. And if you choose from here, for example, orange, it will go to here, to orange. Now this model, this is a real model that is trained, note in here, learn Convolutional Networks CNN in your browser. This is a real CNN running behind the scenes, and it is well trained. If you choose, for example, pizza, it will move the chosen class to a pizza. Okay, if you increase this, we have now here pizza. If we click on pizza now, we have this hidden flattened layer, because when we pass the outputs from the input layer to the convolution layer, the convolution doesn't work with 1D data. There is a convolution now works on 1D data. There is a conv1D layer that operates on 1D data like text. This is used for NLP, for natural language processing, or time series when we have just one-dimensional data. But in images, we have conv2D layer. This is a conv2D layer. Notice in here, convolution 2D or conv2D applies a 2D convolution over an input signal composed of several input planes. What are these input planes? Input planes, they are channels. We have red channel, green channel, and blue channel. So we have so the input signal is composed of several input planes, and this is the formula behind convolution. Oh, this is the equation of the convolution. Note that it's simple. We have output equals, or the y equals, so we have this. It's similar to the linear regression equation. We have y equals, so the output equals bias, which is a b, okay, plus, so this is the bias term, plus the sum of the multiplication of weight by the input. So we multiply W by X. When we multiply X by W plus bias, this gives me the result Y, which is the prediction or the output. So we have, if we go into here, we have this important idea. We have biases that are initialized randomly. We have weights that are initialized randomly. We have some input images. We pass these images forwardly in a forward propagation. The model starts crazy. The weights are random. The biases are random. Everything is terrible, horrible. These images are being classified in a wrong way. So a bus image is multiplied by some weights and then added on by some bias. It classifies in the first forward pass. It classifies all images in the wrong way. So I have bus as orange. We have, for example, this cup as pizza. We have all the thing mixed around, and then by using the power of great algorithms like backpropagation and gradient descent, which is the engine of AI, or the engine behind deep learning is backpropagation and gradient descent, we optimize these weights and biases to better represent the inputs and hence get better outputs. Okay, so now we have this flattened layer. This flattened layer contains 1,690 neurons in it, and these are all neurons. And the purpose of using the flattened layer, so each flattened layer here, we have pixel value. We have all these pixel values. Okay, if you try to move this, it is moving it onto here, and then if you finish from this, it will go to the here. Okay, to the next one, and so on, so on, so on. Because it is so long, they cannot do it for all. But here we have this for this one. So they have shortened it to just the first neuron and the last neuron, because it would be a long list of all these connections. And then we have these connections for this convolution into here. If you try to do this, we have this kernel moving across the image. Now the purpose of the flattened layer is to convert this 2D matrix, which is now of size 13 by 13 by 10, to turn it into a 1D vector, which is also 1,690. If we try to multiply 13 by 13 by 10, multiply 13 by 13 by 10, we will get 1,690 neurons. So we have converted these tenses, these multidimensional tenses, into 1D vector, into one long vector called feature vector, which is the vector that contains the features. And then we pass this long feature vector to a softmax function, and this softmax activation function produces what is called as a probability distribution. So if you read here, what is softmax? Softmax is a function, is a mathematical function that converts a vector. So it takes a vector, not a tensor, not a matrix. Takes a vector, converts a vector of k real numbers into a probability distribution of k possible outcomes. It's a generalization of the logistic function to multiple dimensions. So it's kind of it is like the sigmoid or logistic function, but it works for multi output or multi-class classification, and is used in multinomial logistic regression. The softmax function is often used as the last activation function of a network to normalize the output of a network to a probability distribution over predicted output classes. So this is softmax function, and then if you click on this softmax, we will have this kind of window, and it applies this equation, which is the exponential of some value, some logit. This is a logit. This is an unnormalized value from the model, and we divide it by the sum of all exponentials. If you try to hover over this, this is the exponential of the first, this is of the second, the third, the fourth, the fifth, and so on, so on. And here we have logit. Now notice, yes, now the result of this equation is 0.98. So it thinks, the model thinks that it's a pizza by this probability. So the model is saying now, I think that this image belongs to the class pizza by this amount of confidence, which is 0.98 confidence rate. Okay, and now we have here logit before normalization. So the model's raw outputs are called logits, and then these logits are unnormalized scores, are unnormalized or unbounded scores. As you can see in here, their values are unbounded. We have 11.26, we have 5.54, we have 5.11. We have minus values, we have negative values, we have positive values, we have negative values. But after applying softmax, all values will be positive, and all values will be bounded between 0 and 1. So logits are unnormalized. So here, softmax score for pizza. If you try to go to a different, here I have a question. Why do we have, or why do the model say that this is a pizza? Because all the values in here are less than 11.26, 11.27. The largest logit, the largest or the biggest or the highest logit value here is 11.27, and this logit relates to a pizza, while the logits for example, this logit is for a lifeboat, which is 5.54, a small value, 2.9697. This is for ladybug, and then we have 11.27, the biggest value. So this is the biggest value score, the biggest logit, and hence the model will choose the biggest value, which is pizza. If you hover over this, it will say that it is pizza. And note the colors in here. The colors in here, or the degree of the colors, represents the how much the model thinks that it is the class. So this class koala, if we say here koala, it's just a yellow class, mean that it is the model is less confident that this image relates to a koala, while the model really thinks that it's a pizza. It's a really dark circle here, and it also thinks that by a really high degree, it thinks that it is a school bus. Okay, we have here a much redder circle. Why? Because this, if you have over this, you will note that we have this circle relates to this value 5.99, while this circle of koala relates to this value. Oh, it's minus 14.26. So that's why this circle is not going into the red region, because the model doesn't really think that this image relates to a koala, because the logit in here is minus 14.26. Okay, and then for example red panda, this value minus 3.88. Also this circle is not red, is not reddish. So for example this red orange is kind of red, because the value in here is positive 5.11, but the highest value in here is 11.27. That's why the model has chosen that this class is pizza. And if you zoom into here and choose for example this, and the bias, we have a bias here. If we go into here, we have a bias of minus 0.0421, and the chosen class is the class that has this border under it. The chosen class is pizza by this amount of confidence, 0.98. Okay, so this was the explanation of the tool CNN Explainer, and we have explained a lot of the parameters and concepts behind these layers. For example, ReLU layer, conv layer, and the max pool layer. Each layer does a mathematical operation that helps to reduce the representation of the image to better represent the high dimensional data into a small vector space that can generalize well, or the model can discover the most generalizable patterns of the images. So that was it, or that's it. See you in the next lecture or in the next tutorial.